Okay, so I know that this says lesson 2.1, but just pretend that it says lesson 4.2. Okay, we're on lesson 4.2. Homework for this lesson is 4.2. I've just taught this lesson before in a previous semester, and that was the order that we went in. So just flow with it. It is the exact same lesson. I just don't have time to rewrite the lesson and put a new title. Okay, so this is lesson 4.2, which is characteristics of quadratics. Okay, so we know that a linear function looks like this in terms of the equation. Degree 1 on the x, whereas a quadratic has a degree 2, right? And so let's just consider a situation. Justin is standing on a cliff that is 16 feet high. And so I drew Justin right about here, and I drew the cliff starting from the 16. I don't know if you can see that, but you can use your imagination. He throws a stone in the air, and it follows the path shown on the graph below. So he's going to throw the rock in the air, and then obviously gravity is going to pull it down to the ground. Okay, now if you'll notice the x and y axes, they have labels, and so the y-axis represents the height and the x-axis represents what they call a horizontal distance. And when they say horizontal distance, they mean it is the distance horizontally from where Justin is. So Justin's starting from this position right here, and then this is how far the rock is from him and his starting position. Okay, now if we're going to do a first and second differences table, please ignore this big circle. Okay, we're just going to fill out all the y values. These are all of our x values. Okay, so they said x is 0, and when x is 0, we're going to go to a height of 16. And so that's where the 16 comes from. And then at a height of 1, so in other words, like 1 feet away from him, the rock at 1 foot away from him horizontally is at about, I would say, like 21. Do you see that? Like 21 feet. And that's how I got all of these numbers. So you'll notice at like 8 meters or 8 feet from him, so horizontally 8 feet from him, which is right about here, the stone is on the ground, and therefore the height is 0. Okay, now from there we're going to calculate all our first and second differences. So remember that we're taking the bottom number, subtract the top number, and so if I take a look at all of my first differences, they are not the same. If they were the same, it would be linear and I wouldn't even do this section. But because they're all different, it is not linear, and therefore we do it again in the second differences table. So we take the 3, subtract the 5, so 1, subtract the 3, and we get all of our second differences, and notice that they're all the same number of -2. Since these are the same, it's a quadratic. Okay, so I was showing my previous class that if these were all the same, it'd be linear. If you want to, for your own notes, you can put that these are not the same, and therefore it's not linear, just so that you don't confuse yourself. Okay, now let's answer some extra questions. State the vertex. When they say the vertex, they mean the tip of the parabola. And so the word parabola represents the shape of a quadratic function. So it's pronounced parabola, not parabola. It sounds like a disease, okay? Parabola. All right, so this is a parabola or parabolic shape, okay? And when they say the vertex, they mean the very tip of the parabola, which is at a coordinate of 3 and then a y coordinate of 25. So we put that in brackets with the comma in between. Now, what does the vertex represent? In this situation, it represents a maximum height of the throw of the stone of 25 feet, and it happens 3 feet horizontally away from Justin. Does that make sense? Okay, so this position right here is horizontally 3 feet away from him, but up at the height of 25. So it is a maximum height of 25 feet, and it's reached 3 feet horizontally from him. Okay, next, state the y-intercept. So looking at the y-axis, it's intercepted right here, and that's a number of 16. So what does the y-intercept represent? Sorry. It's the initial height of the stone's toss or the throw. So the stone started off here. It can't start off back here because that's like negative numbers, and that's where the cliff is, right? So the stone starts here and then is thrown off. So this is the initial position of the stone. And that's how we decode like y-intercept into like we reference it in terms of what the question is talking about. So the question is talking about stones, and that's why instead of saying y-intercept, we actually mean the initial height of the stone. Okay. State the zero. When they say zero, it's another word for x-intercept. So do you see how like the x-intercept is right here? It would be at 8, 0. That is the coordinate. Now what they're going to ask you is a question, but they want you to reference the situation, the scenario. What does the 0 represent in this scenario? So it actually means that that's when the stone landed on the ground. That's all you have to say. So you can say that it landed 8 feet horizontally from him, but basically we're talking about the on the ground portion. Add the axis of symmetry. So that's a new phrase. An axis of symmetry is essentially kind of like a mirror line. So what you want to do is you want to take a look at your parabola and kind of cut it in half. And we only cut it in half vertically. The axis of symmetry is never drawn horizontally. So it just splits the parabola right in half, and it always goes through the tip, so the vertex. Oh, why don't I also tell you, normally this line goes on forever, so I put like arrows on the top and bottom, and I always do it dotted, okay? It doesn't really matter if you do it dotted or not, that's just the way I do it. Use the axis of symmetry to determine where the other 0 of the graph would be. So what they're saying is that, do you see how, like, if this is the mirror line and one of the zeros or x-intercepts is right over here, you can kind of be able to count. See how it's like from here to here, that's about 5 blocks. So you should be able to figure out 5 blocks this way where the other 0 should have been. And if you take the parabola and you just continue the pattern down, it would have connected at this point because it's symmetrical. And that's why we call it an axis of symmetry. Now this is what we call the base graph of just x squared, a quadratic. So this is like no extra numbers, no extra fluff. It's just, this is the bare bones x squared graph, which means that if I just choose numbers to put into x, like -3, -2, -1, 0, 1, 2, 3, we kind of use those as our general numbers. There's some negatives there. There's a 0 and some positives. So what I'm doing is I'm saying, okay, at an x value of -3, which is like right here, do you see how I made my graph, by the way? I was too lazy to put all of the numbers. And so I really don't like it when the students like stop halfway and they just put -2, but they don't write the rest. I figured out a way where you can be like somewhat, you know, like you put all the numbers there, but you don't have to put every single number there because it gets kind of cramped. Just do every other number. But notice that like I know where -3 is. So what this is asking is if -3 is here, how high is the dot? And so you'll have to calculate that. You take -3, you put it into the x and you square it, but make sure that when you're squaring it, you put brackets around the -3 or else you're going to get a -9 as an answer. Okay, so like at -3 x value, you're going to have a y value of 9. So -3 is here. You're going to go all the way up to 9 and put a dot. Right? And so you do the same thing, -2, you're going to put it into the x, you're going to square it so that you get your y, which is 4. And so a coordinate is -2 and 4. So here's -2 and I go up to 4. So I put a dot right there. And there are 1, 2, 3, 4, 5, 6, 7 coordinates. See? 1, 2, 3, 4, 5, 6, and 7. So you'll notice that it's pretty symmetrical. All right? Now, other things that we want to put onto our graph just to make sure that we get all the marks for communication are, you have to, number one, put your scale on both. Okay? Don't stop halfway. All right? You have to label your x and your y axes. You're going to have to draw your curve, right? Your parabolic shape, your quadratic. Make sure that there's arrows on the ends because I could have gone to -4 and gotten the answer 16, and that would have created like another dot somewhere up here. Okay, so it does go on forever upwards, and that's why I put the arrows on either side. Then we also label our graph with the equation, always. Okay, so this is going to now ask us to define certain characteristics of the general x squared graph, which is number one, tell me about the vertex. Well, for the general x squared graph, the vertex is always 0, 0. The axis of symmetry is that line that we said cuts it, like that mirror line that cuts it right in half. Okay, and it has an equation. So do you see how it kind of like cuts through the x value of 0 right there? Then we say x equals 0. So if this green line were over here at the 4, it would say x equals 4. But you always have to write that x equals because this is the equation of a vertical line. Okay. Direction of opening means, is it opening upwards, like does it go on forever upwards, or is it flipped upside down and going downwards forever, which it could. So this answer is either up or down, and in this case it's going up forever, so we say it's opening upwards. Lastly, the maximum or minimum value. So what they mean by that is, do you see how it goes up forever? There is no maximum value because it goes up forever. But there is a minimum value, which is this part right here. The vertex is actually the lowest point of the graph, and it happens at a height, so at a y value of 0. And that's why we say it has a minimum of 0. Now, if it were upside down, then it would have a maximum point, but it would open downwards forever, and so there would be no minimum value. So we would say a maximum of, and then wherever the vertex hit, all right, would be the maximum height. Now, just going through some of the terminology, again, zeros mean x-intercepts, so we're talking about these two coordinates at the x-intercepts. Those are zeros. Okay, we also call them roots, x-intercepts. Axis of symmetry is that mirror line. Okay, and we write it as x equals 2, and then whatever number it cuts through on the x-axis is the number that goes right here. You know the vertex is the tip, and we write it as a coordinate. Okay, maximum means, like if it's upside down, it goes through a highest point, a maximum, but if it's right side up, like normal, like a happy face, that bottom point is called the minimum, and so that is called the lowest point. Right, and right at the very top is this new form that I wanted to show you that a quadratic is written in. This again is called vertex form. Okay, normally there are numbers where the A, the H, and the K are, and so see, I put a 3 for the A, a 4 for the H, and a 5 for the K, and so this, if we look at it, is what we would normally see as a quadratic function. And again, that little 2 is a dead giveaway that it's usually quadratic. Okay, so again, this is called vertex form. You'll see it a lot later. Now, the very last one is just remembering that second differences. So if we do the first and second differences in a table of values, if all of the first differences are the same, you have a linear. But if you do all the second differences and they're the same, you have a quadratic. Okay, so this page is pretty much all about terminology so that you have some new words that you know for this new unit. I didn't say that very well. Let me try again. These new words that you're learning, the terminology, basically are what describe bits and parts of what a quadratic function looks like. So its characteristics.